In a disaster scenario, robots that deal with unpredictable terrain and adapt to their surroundings can more robustly move and reach their goals. Soft robots, which adapt through the use of compliant materials like the Vine robot shown here, are one such type of robot. Since the robot often deforms based on the environment, this also opens up an opportunity to use deformation as a form of sensing. This may be beneficial in locations where more traditional vision-based sensing is restricted. My name is Eugenio Frias-Miranda, and in this work titled Vine Robot Localization via Collision, we present a method to use measurements of collisions during vine robot movement to recover the grown shape. To accomplish this, we focus on solving two problems. First, we developed a set of equations to relate features of collision to the shape of the robot over time. Second, we design a sensorized end cap carried by the Vine robot that measures the collision features needed for localization. To start, we consider the general state of the growing robot when contacting the environment. The robot can contact an obstacle at its tip, and it will bend around obstacles contacting the body. Obstacles on the body we call the pivot points. To localize the tip of the robot using contact, we note two important relationships. First, as shown here, the internal restorative moment of an inflated beam that is buckling is related to the geometry and the pressure. Solving for the free length, we can calculate the distance to the buckling point using known values by measuring the transverse force. Second, the end position of the robot can be calculated from the location of the pivot point, the heading angle of the robot, and the free length. Together, these equations allow us to iteratively estimate the pivot location and calculate the tip position of the robot. To use these equations, we need to be able to sense the necessary features of the collision, which are the force of the collision, the heading angle, and the length of the robot. This is achieved through a cap on the growing robot, along with a sensorized environment, which allows for higher quality force sensing. The combination of a force sensor within the obstacle and a set of contact switches on the cap allow for the transverse force applied to the robot to be detected, while the heading angle is recorded by an IMU also located on the cap. Finally, the robot length is sensed from the base using an encoder. We test the accuracy of this approach for a single contact while varying the environment. We vary the obstacle angle and the pivot location over our range of tests. Here we see a sampling of test results, where we measure the contact angle, the orientation angle or heading angle, and the transverse force over the length of the robot. From the sensor readings, we can estimate the location of the pivot and as a result, reconstruct the tip position. Looking at the path as the obstacle angle and the pivot location change, we can see that the localization matches the changing wall angle well, and follows the position of the wall. As a note, the position here is measured from the center of the cap, so this explains the gap between the position estimate and the true location of the obstacle. To judge the accuracy of our estimate, we calculate the root mean square error of the path estimate relative to the true path of the robot. Looking at RMSE versus pivot distance and versus obstacle angle, we can see that the RMSE remains below 5 centimeters in most cases. We observe a slight increase in RMSE with lower values of obstacle angle. Finally, to demonstrate our localization model, we tested it over 3 obstacles. The approach is able to precisely track the robot's journey despite the multiple contact changes. We observed a maximum of 20 centimeters or 5% of the full-grown length. The error increases with each change in obstacle contact, indicating that future work should focus on improving the accuracy of the pivot estimation. Thank you so much for your attention.